Okay guys, next we are going to introduce another two coordinate systems for three-dimensional space which help us calculate the triple integral easier. In particular, when we are talking about the substitutions in triple integral. Okay, so these are the first. We are going to talk about cylindrical coordinate system and then a spherical coordinate system. These are two new coordinate system for three-dimensional space. So starting with cylindrical coordinate system. Okay, look at here. You suppose that we have a point in three-dimensional space like x, y, z. Okay, like x, y, z, something like this. X, y, z. So you can imagine this is x, y, z. So suppose that this point drops onto xy plane. When it drops onto xy plane, so we have here x and y, right? Okay. Or simply you just consider the first two components, x and y, here. So when this point drops onto xy plane, so we have a point in xy plane or two-dimensional space. X and y, okay, these are the components or coordinates of this point here. So simply you just convert this x and y to r and theta. It means you get the equivalent polar coordinate of this point, which will be r and theta by using these two equations. So when you get the polar, the coordinates of this point, again return this point back to its place. It means this point is xyz, right? Drops here, so xy will be converted to r and theta, then back to its place, so become r theta z. So you can see here xyz, only xy will be converted to r and theta, z is the same. It means you can see here they mention z in cylindrical and Cartesian coordinate system is same. It means we just convert x and y to r and theta, or conversely r and theta to x and y. Z is the same. So that's it. This is the story of the cylindrical coordinate system, and you can see, like, using these equations, we convert r and theta and z, it means cylindrical, to Cartesian, and using these three equations we convert Cartesian x, y, z to r and theta and z. Okay, that's it. So now next, okay, next we are going to learn about the surfaces of three simple cylindrical equations. You can see, actually, when r equals constant, when theta equals constant, and when z equals a constant. Starting with r, when we say r equals r0, it means r is constant. This is a cylindrical equation. But what is the surface of the cylindrical equation? Okay, you can see r is constant, right? R is constant, and the equation is independent from theta and z. Okay, you imagine if you have r equals r0 in two-dimensional space. Do you remember this is a circle centered at origin of radius r0, right? But we are talking about three-dimensional space, so we can say, since this equation is independent from z, you can imagine that we have a line parallel to z-axis. Okay, we have a line parallel to z-axis which is moving around this circle. So what do you see? A cylinder. Okay, so r equals r0 is a cylinder. Okay, this one in purple color, and you can see z is the central axis and r0 is the circular radius. Second, z equals z0. Simple. Do you remember we said that z in Cartesian coordinate system and the cylindrical coordinate system is the same. So when we say z equals z0, it's a plane. It's a plane parallel to xy plane which is passing through z equals z0. This one, simply, it's a plane. Okay, when they say circular surface, actually it's a plane, because this equation is z is fixed. It is independent from r and theta. So r could be anything, and theta, for theta we can rotate. So you can see it covers like a two-dimensional surface parallel to xy plane, which is a plane z equals z0. Okay. And so it's just a plane. Now theta equals theta 0. Theta equals theta 0. Okay, here you can see the typo. This is actually theta equals theta 0. Okay, again, imagine what is the if we are talking about the equation of theta equals theta 0 in two-dimensional space in polar coordinate system. Do you remember, this is a line? Okay, this is a line passing through the origin, making theta 0 angle with positive direction of x-axis. But here you can see this equation is independent from how to say z and r, especially z. So actually when we say theta equals theta 0, you can see here, this is actually the surface of this equation is a plane. In the red color you can see it's a plane, is passing through the z-axis, right, and making theta 0 angle with xz plane. Okay, you can see, and of course this the red the green plane, of course, is perpendicular to xy plane. You can see here, perpendicular to xy plane. Okay, so they say it's a surface. Actually, this is a plane. Okay, this is a plane perpendicular to xy plane, parallel to z-axis. You can see like it's passing through the z-axis and making theta 0 angle with xz plane. So these are simple. Of course, we have more complicated, cylindrical equation, but for us, at least we should know these three simple cylindrical equations. Okay, next, okay, here we want to calculate the triple integral in cylindrical form or in cylindrical coordinate system. What does it mean? Look at here. Previously we have a triple integral like f of x, y, z on region D dv, right? Okay, so we know that if we have a f of x, y, z dv on region D, dv in Cartesian coordinate system is dx, dy, dz, the product of these three elements. But since we introduce another coordinate system for three-dimensional space, which is cylindrical coordinate system, so this time we might have a function of r and theta z. It means we have a function of three independent variables, or let's say a function of points in three-dimensional space using the cylindrical coordinate system. So we have f of r and theta and z. So we want to know how to calculate the triple integral of f of r theta z on a bounded region D dv. Okay, first of all, okay, if you are using cylindrical coordinate system, in cylindrical coordinate system dv equals, bear in mind, do not forget, dz r d theta. So totally it means when we are calculating f of r and theta and of f of r theta z dv in cylindrical form on D, this equals f of r theta z, this is dv, so this equals r dz dr d theta. Okay, so next we are going to see how to describe the region D when we are using the polar coordinate system. Then when we set up the integral correctly, then we can integrate first with respect to z, then with respect to r, then with respect to theta. Again, be very careful, this is not the only order, but usually in this course for you, the integrals will be set up in this order, dz dr d theta. Okay, look at next. Okay, now look at here how we are going to describe the region D uh, in cylindrical coordinate system. Usually, okay, this is not the only case, but I said usually in this course the region D will be described in this way. Be very careful. Look at here. Do you remember that when we are talking about the description of the region D in Cartesian coordinate system, do you remember we used to say uh, Z is from a lower surface to upper surface? Of course, when we are using Cartesian coordinate system, the lower surface will be of this equation. Z equals f1 of x and y to f2 of x and y. But here we are using cylindrical coordinate system. It means you have to convert the equation of lower surface and upper surface into cylindrical coordinate system. So the equation of lower surface will be z equals g1 of r and theta. The equation of upper surface will be g2 of r and theta. Do you remember? Just compare it with Cartesian. With Cartesian, we say in Cartesian coordinate system, we say from f1 of xy to f2 of xy. Here we are using cylindrical coordinate system. So we say the lower surface and upper surface must be converted to cylindrical. So z is from g1 of r and theta to g2 of r and theta. Okay. Now look at the, okay, this is for z. This is for z. Now look at the image or the projection of this region D onto xy plane. Let's move on to the next page. Okay, look at the image or the projection of D onto xy plane. Of course, the projection will be a bounded region in two-dimensional space. Now you try to describe this bounded region in two-dimensional space using r and theta. It means using polar system. So do you remember, to describe this we say r is from some inner radius or inner curve to upper curve. Here you can see it means r is from the inner curve, which is like h1 of theta, to upper curve. Okay, better I say from inner curve with this equation h1, r equals h1 of theta, to outer curve like r equals h2 of theta. So this is for r. Okay, and then to cover this region, theta must rotate from, like, let's say theta is from alpha to beta. You can say theta is from alpha to beta. Okay, so this is how we set up the integral. You can see f of r theta z dz r dr d theta. Then z is from g1 of theta to g2 of g1 of r and theta to g2 of r and theta. R is from inner curve with this equation h1 of theta to outer curve h2 of theta. And the theta is from alpha to beta. So this is how we set up the integral in cylindrical coordinate system. So the rest is the same. We start first integrate with respect to z. What is left will be a function of r and theta, then with respect to r, then with respect to theta to find the answer. So be very careful. Okay, you can see here. Okay, now look at this example. We want to set up actually a triple integral in cylindrical coordinate system. It means like let me show you. We have a triple integral of f of r and theta, r theta z, dv on d. Now, okay, first of all, we know that dv is dz r dr d theta, or doesn't matter. Eventually, it means dv is r dz dr d theta. But what is the region D? You can see here. This is the region D. Okay, the bounded region D. So you can see the okay, from below, this is bounded by xy plane or we can say a portion of z equals 0, like if we are using Cartesian system. So z is from 0 to this plane. What is the equation of this plane? Z equals 2 minus y. But listen very carefully. We are going to describe this region in cylindrical coordinate system. So z is from 0. Okay, z equals 0 is a constant function. Okay, so this will be the equation in cylindrical. Z is from 0 to z equals 2 minus y. Now we have to convert this one, like the equation of, okay, z equals 2 minus y. We have to get the cylindrical equivalent cylindrical equation of this surface or plane. So you can see I have done it here. I have done here for you. So z is from 0 to z equals 2 minus y. Okay, so this equals 2 minus, but what is y? R sine theta. So it means z equals 2 minus r sine theta is the cylindrical equation of the upper surface. So lower surface, z equals 0, upper surface, z equals 2 minus r sine theta. Okay, and then look at the image of this region D or solid into xy plane. The image of this solid onto xy plane will be this right angle triangle. Okay, look at the next page. Now we have to describe this right angle triangle, or simply this triangular region, bonded triangular region, using r and theta, or in polar form, using polar coordinate system. So since this line is y equals x, okay, this line is y equals x, so this theta will be 45 degree or pi over 4. So it means theta is from 0 to pi over 4. Okay, what about r? So do you agree with me to cover the region, this triangular region? Theta, r must be from 0 to this line. So r is from 0 to this line. What is this line? This vertical line. This is, let me show you. X equals 1. Okay, now you have to get the cylindrical or polar equation of this vertical line. So x is r cosine theta equals 1. So r equals 1 over cosine theta. So it means actually here r is from 0 to this line. But what is the polar equation of this line? 1 over cosine theta. So you can see everything must be converted to cylindrical or polar. So now we can set up the integral. Okay, z is from 0 to 2 minus r sine theta. R is from 0 to this line, but the polar equation of this line is r equals 1 cosine theta. So r is from 0 to 1 over cosine theta. And theta is from 0 to pi over 4. Okay, f of r and theta and z, and this is dv. Okay, here the formula of f is not given. If it is given, we can go ahead and calculate the integral. But as I mentioned earlier, the point is to set up this triple integral correctly. But shortly later, I will give you some example. Then we can calculate or evaluate the integral till the end. Now look at the next example. Okay, now let's look at the another example. Again, we want to set up a triple integral. Let's say we have a triple integral of, you can see here in the next page, triple integral of f of r theta z dv. Okay, dv in cylindrical is dz r dr d theta, or, and this equals r dz dr d theta on region D. But what is the region D? Region D is this. Okay, look at here. We have a cylinder here with this equation. Cylinder. Look at here. X squared plus y minus x squared plus y minus 1 squared equals 1. Why I say cylinder? Because we are considering all these equations in three-dimensional space. Of course, this x squared plus y minus 1 s squared equals 1 in two-dimensional space is a circle. You can see here. It's a circle centered at 0 and 1 of radius 1. Okay, this is the center. And of course, because the equation is independent from z, so you consider a line parallel to z-axis, and this line is moving around this circle. So you see a cylinder. So this is actually this cylinder in blue color. And we have another surface here, z equals x squared plus y squared, which is called paraboloid. Okay, paraboloid. Okay, paraboloid, something like this. A paraboloid, something like this. Paraboloid. Okay, so the region D, roughly saying, is bounded between this paraboloid, okay, this paraboloid, this one, and this cylinder. Okay, so we want to describe this region D to set up our integral. Okay, look at here. If you are using Cartesian coordinate system, we say z is from 0 to upper. Okay, z is from lower surface, which is xy plane, a portion of xy plane, with equation z equals 0, to upper surface. What is upper surface? Is a portion of this paraboloid, z equals x squared plus y squared. But as I mentioned, everything must be converted to cylindrical. So z equals 0 is the same. From z from 0 to z equals x squared plus y squared. This one must be converted to cylindrical. So in cylindrical, x squared plus y squared equals r squared. So it means the cylindrical equation of this paraboloid is z equals r squared. So we can say z is from 0 to r squared. Okay. Now, what about what about r and theta? Okay. Next, we have to get the image or the projection of this region D onto xy plane. The image or the projection of region D onto xy plane will be this circle. Okay, you can see here they show circle centered at 0 and 1 of radius 1. And the equation of this circle, Cartesian equation, is x squared plus y minus 1 squared equals 1. Now, we have to convert this the Cartesian equation of this circle to polar. Why? Because we are going to find the limits for r and theta. So here you can see, to cover this circle or describe this circle using r and theta, using polar coordinate system, you can say, okay, for theta it is d. To cover this region, you can say theta is from 0 to pi. So theta is from 0 to pi. But what about r? R is from 0 to this circle. So that's why you have to get the polar equation of this circle such that r is a function of theta. Okay. You can see the answer is given here to you, what I have done. So let's find the polar equation of the circle. You can see our circle is x squared plus y minus 1 squared equals 1. So this equals x squared plus y squared minus 2y plus 1 equals 1. So 1, 1, 0. So left x squared plus y squared minus 2y equals 0. X squared plus y squared equals r squared minus y is r sine theta. Okay, so we get this. Now if you factorize r, so we have r times r minus 2 sine theta equals 0. So either r is 0 or r minus 2 sine theta equals 0. So from here we get r equals 2 sine theta. This is the main equation that we are looking for. Why? Because this equation is included here. Why? Because when theta is 0, r equals 0. So this equation is included in this equation. So r equals 2 sine theta. That's what we are looking for. So let's back here. So r equals 2 sine theta is the polar equation of this circle. So we can say theta is from 0 to pi and r is from 0 to this circle, which is 2 sine theta. So now we can set up the integral. You can see z is from 0 lower surface to upper surface, but the equation upper surface in cylindrical. Z equals r squared. And the image will be an image, the region D will be this circle, and the description of this circle in polar coordinate system is this. R is from 0 to the circle. The equation of the circle, r equals 2 sine theta. And then theta is from 0 to pi. So now the integral is set up correctly. We can go ahead to calculate if we have the formula of f. But as I said again, the main point of this example is to set up the integral correctly. Next, I'm going to give you another example that we are going to solve the integral. Okay, look at next. I prepared an example for you. Look at here. We want to evaluate this integral. F of r theta z is this. Z times cosine theta over 2 dv on region D. Now let me explain to you what is region D. Look at here. We have this paraboloid. You can see here. We have this paraboloid with this equation. Z equals x squared plus y squared. We cut this paraboloid by this plane. The plane z equals 1. So you can see the region D is this. So the region D from below is this paraboloid. From above we cut it with this plane z equals 1. So this is our region D. Okay. So we want to calculate the triple integral of this function on D. Okay. So let's do it. Okay. Let's calculate the integral. Okay. To calculate the integral, first we have to describe the region D. Okay. Now look at the region D. Region D from the below is bounded by this paraboloid. Z equals x squared plus y squared. And the cylindrical equation of this paraboloid is z equals r squared, because x squared plus y squared equals r squared. So z is from lower surface with this cylindrical equation, z equals r squared, to z equals 1. So from below paraboloid to the plane. So z is from r squared, z is from z equals r squared to the plane, z equals 1. So these are the limits for z. Now look at the image of D onto xy plane. Look at here. When we cut this paraboloid by z equals 1, so you put 1 here instead of z. So we have 1 equals x squared plus y squared. So what you see here is a circle, right? Is a circle. So this circle is of radius 1. So the image of this circle into xy plane will be this circle. X squared plus y squared equals 1. It means unit circle centered at origin. So the image of D onto xy plane will be this unit circle. Now how do you describe this unit circle in polar coordinate system? So we have done this. So you can say r is from 0 to 1. Okay, r is from 0 to 1, and theta is from 0 to 2 pi. So these are the limits for r and theta. So now we can set up the integral and go ahead. So look at here. So we have integral z cosine theta divided by 2, and this is our dv, r dz dr d theta. So z is from lower surface, r squared with this equation, z equals r squared, to upper surface with this equation, z equals 1. And then r is from 0 to 1, and theta is from 0 to 2 pi. Okay, the rest, okay, we have r cosine theta, z dz dr d theta. So we are going to integrate first with respect to z, then with respect to y, then with respect to r, then with respect to theta. We will find the answer. Okay. So the first integral with respect to z, so this r cosine theta is a constant. So constant. So integral z dz is z squared divided by 2 from r squared to 1. Okay. So this equals the integral. So this is 1 over 2 or 1/2, right? I take it here. So 1/2 r cosine theta divided by 2. Now, when z equals 1, 1 squared is 1 minus when z is r squared squared r to the power of 4 dr d theta. So this equals this 1/2 moves out is a scalar integral cosine theta and this one look at here r times 1 r minus r times r to the power of 4 r to the power of 5 dr d theta. Okay, so everything correct. 1/2 cosine theta and this time it becomes r minus r to the power of 5 dr d theta. Now we have the next integral with respect to r. Okay, since the space is not enough, let me erase here. So we move up and continue the calculation here. Okay, let's move up here. So we have 1/2 integral cosine theta over 2 r minus r5 dr d theta. So now we integrate with respect to r. So this is constant. So we have 1/2 integral. This cosine theta is constant, so the integral of r is r squared divided by 2 minus the integral of r5 is r6 over 6, r6 divided by 6 from 0 to 1 d theta. So this equals 1/2 integral cosine. So when r is 1, this equals 1/2 minus 1 over 6. When r is 0, this is 0, so only left this. And if we calculate 1/2 minus 1 divided by 6, you can calculate this equals 2 over 6. So this is a constant, we take it out here. So this equals 1/2 times 2 over 6. 2 over 6 is this. 2 over 6 integral from 0 to 2 pi in integral from 0 to 2 pi cosine theta over 2 d theta. So 2 over 2 is 1, so left 1 over 6. Now the integral of cosine theta over 2, you can use substitution. You can take theta over 2 to be u. If you use substitution, the integral of cosine theta divided by 2 equals 2 times sine theta divided by 2. Okay, now 2 over 6 is, okay, this 2 over 6 it means 2 over 6. 2 divided by 6 means 1/3. Now sine theta over 2, when theta is 2 pi, this becomes sine pi, minus when theta is 0 becomes sine 0. So sine pi is 0, sine 0 is 0, so totally the answer will be 0. So the answer to this triple integral on this region D in cylindrical, that we solve it in this function in cylindrical coordinate system. So the answer is 0. Okay guys, next we are going to introduce another coordinate system for three-dimensional space, which is called a spherical coordinate system. This spherical coordinate system for every point, for any point in three-dimensional space is denoted by 3 values: rho, phi, theta. Okay, you suppose that we have a point like P with Cartesian coordinate x, y, z in three-dimensional space. Okay, this is P. So look at this line segment OP, okay, which is connecting the origin and the point P. So the distance between P and O, or O and P, the distance from the origin to point P, is called is denoted by rho. Now look at this line segment OP. It makes some angle, right, with positive direction of z-axis. We denote this angle by phi, okay, by phi. So this is rho, the distance, and this one phi. Now look at the the image or the projection of this line segment OP onto xy plane. So the projection of this line segment onto xy plane is this line, okay, line segment. The distance or the size of this line segment is denoted by r. Now look at here, this line segment is making theta angle with positive direction of x-axis. So we got rho phi theta. This triple of rho phi theta is called the spherical coordinates of the point P. Okay. So you agree with me, if we know rho phi theta, we can find the position of the point P. Like if we know rho, we know what is the distance of P to the origin, and if we know phi, we know what angle it is making, and if we know theta, we know that where to stop, like when we are rotating like this. Okay, I have to mention something about the boundaries or bounds or lower limit and upper limit, or better I say about the boundaries for the values of rho phi theta. You can see we said that rho is the distance to the origin, right? So rho is always greater than equals 0 because it's the distance. Theta is between 0 and 2 pi, okay? Theta is between 0 and 2 pi to cover, okay, all. And phi is between 0 to pi, okay? Phi is from 0, you can see phi is from 0 to pi. Actually, when phi is from 0 to pi over 2, it is going to cover positive z, and when phi is from pi over 2 to pi, is going to cover negative values of z. So be very careful about these things. So on the next page, you can see the relation between Cartesian coordinate system and a spherical coordinate system. You can see, actually, okay, here there are the equations. You can see the equations that we can go from Cartesian to a spherical. It means if we are given x, y, z, we can find rho phi theta like this. Rho is the root of x squared plus y squared plus z squared, or equivalently we can say rho squared equals x squared plus y squared plus z squared, because rho is the distance of the point x, y, z to the origin. Okay. Now look at here, what is r? Okay, r is the image of this line segment OP onto xy plane. So this is r. So you agree with me, here we have a right angle triangle. So r equals the root of x squared plus y squared, or equivalently we can say r squared equals x squared plus y squared. How we can find the theta? Okay, look at here. So in this right angle triangle, tangent theta equals y over x. So theta is arc, or arc tangent, means tangent inverse y over x. And also we have another right angle triangle. Look at here, if I connect this, if I have a line from here, okay, perpendicular to z axis, so this value is z. So in this right angle triangle, okay, tangent phi equals what? What is this one? The size of this side is r, equals r. So tangent phi equals r, okay, divided by z. So using this we can, so phi is arc tangent, or tangent inverse r over z. We can find the phi, okay. Here below you can see the equations that we can move from a spherical to Cartesian. It means if you are given the spherical coordinate of some point, spherical coordinates of some point in three-dimensional space, we can find the Cartesian. Look at here, starting with z, in this right angle triangle, look at here again, in this right angle triangle, this is z, right? So you agree with me that, okay, and this is rho, that z, okay, so because rho phi theta is the spherical, so but for Cartesian we have x, y, z, so this amount is z, okay, the third coordinate of Cartesian system, Cartesian coordinate system, Cartesian coordinates of the point. So z equals this in this right angle triangle. Z equals rho cosine phi here. Okay. And then look at here. So this side is, which is z, rho cosine phi. And now this side of this right angle triangle, what is this? Rho sine phi. But this rho sine phi is actually r. Okay, these two are the same. So rho sine phi is r. Now look at the, you can see here, rho sine phi is r. Now look at this right angle triangle here. In this right angle triangle, x is r cosine theta. X is r cosine theta. R cosine theta. But r is rho sine phi. And y is r sine theta. R sine theta. But r is rho sine phi. So totally, we have x equals rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi, and r is this, rho sine phi. Sometimes to find phi, find phi here, instead of this, we may use this equation to find phi. Okay. So, and you can see here, of course, as I mentioned earlier, we are introducing the cylindrical already and a spherical coordinate system to help us calculate the triple integral easier. Soon later you are going to see that we are going to use this two new coordinate system for our substitution. And you can see here later you are going to see what it means, that this coordinate system, a spherical coordinate system, help us calculate the integral on a spherical region or conical region easier. So let me give you an example about this. Okay, look at here. I provided an example for you. We are given the Cartesian coordinates of a point like P in three-dimensional space. You can see here x, y, z. We want to find the spherical coordinates of this point. Okay, spherical. So look at here, let me remind you, we have to find rho phi theta. Okay, rho equals the root of the square root of x squared plus y squared or z squared, or equivalently we can say rho squared equals x squared plus y squared plus z squared. So this is x squared, y squared, z squared. So when we calculate, this will be 2 plus 2 plus 12 divided by 16. So 16 divided by 16 is 1. Look at here, this is rho squared. So we just take a square root on both sides. So rho equals the root of 1, which is 1. Remember, rho is non-negative, so we don't have to put positive, negative. So rho is always positive. Then theta. Theta is the tangent inverse of y over x. This is y, x. This is x, this is y. And you can see y and x are equal. So y over x becomes 1. So the tangent inverse of 1. So we are looking for an angle whose tangent is 1. And this angle theta is between 0 and 2 pi. Look at here, the point is located in the first octant. So the image of the point onto xy plane is located in the first quadrant. So we are looking for theta whose tangent is pi over 4. So we have two answers here. One is pi over 4, the other one is pi plus pi over 4. But since the point is located, the image of the point onto xy plane is located on the first quadrant, or totally the point is located in the first octant. So the answer we are looking for is theta equals pi over 4. Now we want to find phi. Okay, remember this phi might be written by this or like this. Okay, These are, okay, this is phi, or this one sometimes they may call it, okay, this, I mean the phi might be denoted by this symbol or this symbol. Phi, phi, okay. If you are convenient, you can use this or you can use this. So this is phi, okay. Okay. To find phi, we have to use this. Phi equals tangent inverse of r over z. However, you may use this equation to find phi because you have z, you have rho, so you may use cosine phi to find phi. But okay, we are going to use this. So first we have to calculate r. R is the square root of x squared plus y squared. You can see here. X squared is this. So 1 over 8 plus y squared is this. 1 over 8. So we have 2 over 8, which is the root of 1/4, which is 1/2. Now, phi, as I said, with, you can denote this phi by this or by this, it doesn't matter. Phi equals tangent inverse of r over z. Okay, so the tangent inverse r over z you can calculate will be 1 over the square root of 3. Now, we are looking for an angle like phi whose tangent is 1 over the root of 3. And look at here again. Since z is positive, okay, z is positive, so z is located above xy plane. So it means phi must be an angle between 0 and pi over 2. Do you remember I mentioned when phi is between 0 and pi over 2, z is positive. When phi between pi over 2 and pi, z is negative. So the angle we are looking for is pi over 6, because the tangent pi over 6 is the root and 1 over the root of 3. So here is pi over 6. So rho phi theta. So the spherical coordinates of this point, the spherical coordinate of this point will be rho phi theta, right? Rho phi theta. In your lecture notes, sometimes they write rho theta phi. There is nothing wrong, but this is the correct order. Rho phi theta. Rho comes first, phi second, third theta. So this equals rho is 1, phi is pi over 6, and theta is pi over 4. So this is the spherical coordinate of this point. Okay. Next, okay, here, page 74. We are going to study the surface of 3 simple spherical equations. Starting with this one, when theta equals, phi equals phi 0, it means phi equals a constant. Okay, look at here. When we have phi equals phi 0 constant, it means the points that are locating on this surface, the angle between these points and the positive direction of z-axis is phi 0, fixed. Okay, but the equation is independent from rho and theta, so it means rho can take any value from 0 to infinity. Now the equation is independent from theta, right? So we can rotate. It means theta can take any value from 0 to 2 pi. What do you see? A cone. So remember, phi equals phi 0 is a cone. You can see here in brown color. The other one, theta equals, okay, sorry for interruption. Theta equals theta 0. Okay, so theta is fixed, but the equation is independent from rho and phi. Okay, so it means if we have the points that are locating on this surface, the angle between these points, if these points, if you get the image of this point onto xy plane, the angle between the image of this point, the angle between the image of this point onto xy plane and x-axis is fixed, theta 0, you can see here. But look at here, the equation is independent from rho. So rho can take any value, right? Rho can take any value. And apart from that, look at here, apart from that, the equation is independent from phi. So phi can take any value from 0 to pi. So what do you see? You will see a half a plane actually. A half a plane here in green color. Okay, a half a plane, which is passing through the z-axis, and the angle that they said the angle that it makes between actually we can say like this: the angle between this half a plane and xz plane is theta 0. Okay, they said made angle with xy plane. Well, actually, if the points drop into xy plane, yes, then we can say the angle is theta 0. But we can say we have a half a plane, and the angle between this half a plane, this one, and xz plane is theta 0. So this is a half a plane. The last one, rho equals rho 0. Rho equals a constant. So what does it mean? It means all points, the distance between the all points on this surface to the origin is fixed, rho 0. So every point in this surface, the distance between every point on this surface to the origin is constant, rho 0. Okay, so the equation is independent from phi. So phi can take any value from 0 to pi, and then theta can take any value from 0 to 2 pi. So what do you see? A sphere. So rho equals rho 0. The surface of this equation is a sphere. Is a sphere centered at origin of radius rho 0. Okay. Okay, so remember, rho equals rho 0 is a sphere centered at origin of radius rho 0. Okay, next we have an example on page 75. We are given the Cartesian equation of some surface. You can see actually x squared plus y squared plus z minus 1 squared equals 1, which is actually, okay, here is a little bit typo. Actually, we have to move it one here actually. Okay, it doesn't matter. Okay, it doesn't matter. You have to fix it. Okay. So you can see this is the equation of a sphere centered at 0, 0, 1 of radius 1. We want to obtain the spherical equation of this sphere using these equations. Okay, using actually, yes, this equation. You can see the relation between spherical and Cartesian using these equations. Okay, let's do it. Okay, so now take a look at here. We want to find the, okay, this is the Cartesian equation of the sphere. Now, okay, this x squared plus y squared plus z minus 1 squared is z squared minus 2z plus 1 equals 1. This 1 by 1 is cancelled, so left x squared plus y squared plus z squared minus 2z equals 0. Now we want to convert it to a spherical, right? X squared plus y squared plus z squared is rho squared minus 2 z equals rho cosine phi, so equals 0. And then if we factorize, so look at here, if we factorize rho between these two, we have rho times rho minus 2 cosine phi equals 0. So it is either rho is 0, or rho minus 2 cosine phi equals 0, which is equivalent to saying that rho equals 2 cosine phi. So you can see we have two equations here, but the main equation that we are looking for is this: rho equals 2 cosine phi, because when phi is pi over 2, rho becomes 0. So my point is this sorry, this equation is included here. So rho equals 2 cosine phi is the spherical equation of this sphere. Okay, look at here. We have another example. Actually, Cartesian equation of this cone is given. Okay, here we have to move. Sorry, here, yeah. Okay. Z equals the root of x squared plus y squared. Okay, this is the Cartesian equation of this cone. Okay, we want to find the spherical equation of this cone. But do you remember, totally in general, if you look at some page here that we explained, totally if you have a cone, the equation of the cone in a spherical will be phi equals phi 0. So it means here when you want to find the spherical equation of this cone, must be phi equals some constant. Okay, here you can see the answer. The answer is phi equals pi over 4. But how to find this answer? Of course, to convert the Cartesian equation to a spherical equation, we have to use these equations. Okay, so let's do it. Actually, we can do this using two ways. One is much simpler, another one more complicated, let's say. So I'm gonna explain this one simply for you. Look at here. I have done this here for you. If you remember, tangent phi equals r over z. Do you remember? Now, r equals the root of the square root of x squared plus y squared. And here z, look at here, the Cartesian equation of this cone. You can see z equals the root of x squared plus y squared. So actually r and z are equal. So then tangent phi equals r and z are equal, right? So r over z equals 1. So now, what angle do you know, what phi do you know, whose tangent is pi over 4? But we have to be careful, because phi is, how to say, between 0 to zero to pi, right? So phi is between 0 to pi, right? But look at our cone, because our cone is facing up. Okay, so theta, so phi must be between 0 and pi over 2. If the cone is facing down, then phi must be between pi over 2 and pi. So since here our cone is facing up, let's say facing up, so phi must be between 0 and pi over 2. So we are looking for an angle between 0 and pi over 2 whose tangent is 1, and that angle is pi over 4. So phi equals pi over 4 is the how to say, a spherical equation of this cone. Okay,